So today class, module number 3 as per VTU syllabus given, solidification and non-ferrous foundry practice. So last session you have studied different types of furnace used in the foundry and sand molding, and first module and second module you have completed. So next you can go for the third module as per VTU syllabus, solidification and non-ferrous foundry practice. So what is solidification and what is, before that you can study about that, what is solidification, what is non-ferrous foundry practice. So solidification means, so the solid liquid state of the molten metal is converted into solid state at room temperature. It is called as solidification. Suppose example, so you can first, as per drawing, you can prepare the cavity, mold box. You can use the mold box, you can prepare the cavity with the help of pattern. So once you can prepare the cavity as per your drawing, so you can put into the liquid metal into the cavity to fill the cavity with liquid metal. So at room temperature, it is solidification taking place. After that, open the cope and drag box. After that, open the cope and drag box. So solidified will get the component as per requirement or as per drawing. So this process it is called as solidification. So non-ferrous metal. So already you studied in the first module and second module ferrous metal and non-ferrous metal. So what is ferrous metal and what is non-ferrous metal? There is a question. So non-ferrous metal means the iron content of the metal completely zero. There is no iron content. It is called as non-ferrous metals. Example we can take gold, silver, bronze, tin, lead. So these are the non-ferrous metals because there is no iron content. Suppose ferrous metal means the iron, some percentage of iron content present on that material. It is called as ferrous metal. Example, cast iron, wrought iron, pig iron, steel. So these are the example for the ferrous metal first. So in this syllabus, in this module, so you have to concentrate about the only the non-ferrous metals. Whether you can take aluminium or bronze, gold, silver, tin, lead, whatever it may be. There is no iron content in the metal, so you can practice in the foundry. This is the main concept: solidification and non-ferrous foundry practice. So next, you can study about the what is solidification. That is the question. Solidification is a process. So another name it is called as the phase transformation of liquid metal. Solidification is a process involving the phase transformation of a liquid metal to a solid state. The liquid state of the molten metal is converted into solid state. Clear? The liquid metal liquid metal is converted into solid state. It is called as solidification. So in this solidification, at the time of solidification, the process result is in the removal of the heat from the hot liquid. This process result in removal of heat from the hot liquid metal. So resulting in conversion of liquid to solid. Simple. So remove the liquid metal, the enormous heat will be hot heat will be present on that liquid metal. So you can remove, we will get conversion of liquid to solid. Solidification process is also referred as freezing process. Just you can take an example for the water is converted into ice. So you can put in the water in the deep freezer. The liquid state of water is converted into ice. So here liquid metal is converted into that's why it is called as a freezing process. Clear? So next step is during the freezing of the molten metal in the mouth, the latent heat of the fusion of the metal has to be transferred to the surrounding atmosphere. The heat will be directly exposed or goes to the atmosphere, and the solid liquid metal is converted into, or liquid state converted into solid state. So definition for the solidification. So in this process, conversion of liquid metal at a higher temperature to solid metal. That means, so solid state converted into liquid state converted to solid state at a lower temperature. Solidification involves atoms and their growth. We can study about that. So next go for the cooling rate. So we can see the graph. So clearly understand cooling curve for changing the liquid into solid. How to temperature decreases. You can see the graph. So you see this is the x-axis line. It shows that. So time in minute. So this is a y-axis. It is a temperature. So first is this is a liquid state. This is the highest point in the y-axis. No, this is a the metal is in a liquid state. So gradually decreases this line. So this is, you can see this is gradually the temperature decreases. So some waiting some at room temperature. So after that to reach this point, so freezing will be start. Freezing. So freezing starts from here. So here to here. So we can wait liquid to solid state converted in this horizontal line that indicates the liquid state of the molten metal is converted into solid state. So that point it is called as, so this is a freezing completes either. So here slowly first you can see the y-axis temperature gradually decreases. So at room temperature, so we can wait 30 minutes or 40 minutes. After that, so once you can freezing start, so the line it shows that it is a horizontal line. That is a x parallel to the x-axis. The liquid state is converted into solid state. The freezing will be start here, this point, and freezing completed. So this is a freezing. The solid liquid metal is converted to solid state. Again, the temperature falls down. You can see here. So this is completely coming nearer to the x-axis line. So this is the freezing point substance here. So this point is freezing point substance. Temperature gradually decreases here and freezing start from here, this point. So this point it shows that horizontal line up to starting from to ending it is called as a freezing process is completed. Freezing process is completed. After that the temperature will be slowly falls down here. You can see that. So this is a cooling curve for change the liquid into the solid state. The cooling start from the liquid state into the solid. Liquid state converted into solid state. Temperature centigrade. So you can see this clearly line diagram. So this is the temperature y-axis and x-axis is a time per minute. So you can, this is a liquid temperature, maximum heat temperature. This is a, suppose you can aluminum, you can take 650. The melting point of the aluminum alloy is 650 centigrade up to 700. Suppose cast iron 1350 to 1400 centigrade. So this is the highest point A. And B is the melting point. This is the B is the, it indicates that the melting point. The temperature, there is metal, aluminum or whatever it may be. There is a ferrous metal or non-ferrous metal. The same cooling curve will be same. Only you can change the ferrous metal or non-ferrous metal. And from B to C is a freezing. This is a liquid state converted to solid state. This is horizontal. Again, you can the temperature falls down here. That is a C to D. These two figures it shows that the cooling curve for changing a liquid into solid state. So next you can go for nucleation. So nucleation means, so nucleation. So nucleation, the solidification of the metals occurs by nucleation and growth. It is very important. At the time of solidification, at the time of solidification, liquid metal is poured into the mold cavity and allowed to solidify as soon as molten metal comes in contact with the mold surface. Small tiny particles, small tiny particles, it is called as a crystal. Small tiny particles, it is called as a crystal. The solidification of metals occurs by nucleation and growth when a liquid metal is poured into the mold cavity and allowed to solidify. The small tiny particles, it is called as crystal are formed. So this process it is called as nucleation process. Clear this point? When the liquid metal is poured into the mold cavity, first thing. Second is allowed to solidify, it will take time. Molten metal comes in contact with the mold surface or mold cavity surface. So small tiny particles, it is called as crystal, as formed. This process is called nucleation process. So you can see this figure. There are four important figures given here. So first we can see. So this is a liquid metal formation of a nuclei. So this is a container. The first stage is formation of nuclei. And second stage, dendrist. You can see this is line. This line, it shows that dendrist formation, dendrist growth. So increase that. The dendrist size will be increases in third stage. And finally, the formed grains. Finally, the formed the grains. This is a nucleation, dendrist formation, and growth of the dendrist, and grain formation at the time of solidification. These four figures are very important. The first one is a formation of the nuclei. Second one is a dendrist formation. Third one is a dendrist growth, and finally formed a grains. This process is complete. This is a at the liquid state converted to solid state. These are the four important changes in the liquid metal. Liquid metal is converted into or solid metal. There is a this figure, it shows that. First is nuclei. Second one is a dendrist formation. The dendrist will be growth in this third stage. And fourth stage is finally formed grains. So we will get the final state. So next we can go for this one is a solidification variables. So during solidification variables, solidification of metal and alloy, the following variables are as follows. The first one is a solidification time. That is a very, very important parameter. Solidification time, solidification rate, and temperature gradient and cooling rate. These are the four variables which is very important at the time of solidification, liquid state converted into solid state. Clear this point. First one is solidification time. How much time is taken? Solidification rate, temperature gradient, and cooling rate. So this is a four important variables at the time of solidification influence the solidification process. The following four variables influence the following process. So detailed study one by one. The first one is solidification. So solidification time is a time taken by the molten metal. It is transferred to the solid state, liquid state to solid state. Solidification time is time taken by the molten metal for its transformation to solid state, liquid state converted into solid state. Second important point, smaller solidification time, lower will be the Muji zone, better will be the properties, shrinkage will be reduced. Smaller solidification time is required very less. Lower will be Muji zone, better will be the properties, shrinkage will be reduced. This is very important. And third important point, sand modes are shows higher solidification time. Sand modes are shows higher solidification time as compared to the metal mode. Sand modes are show higher solidification time as compared to metal mode. And fourth important point, solidification time expressed in seconds. Solidification time is expressed in seconds. So solidification time increases UTS and UTS decreases YS. So you can see. So this is a x-axis line solidification time in seconds. Here also solidification time in seconds. So this is a UTS. So you can see gradually the temperature will be decreased, then time will be increased here. So this is a YS. So next we go for solidification rate. Solidification rate means the solidification rate indicates the rate at which the solidification is progressing from one point to the another point. It is very important. Solidification rate indicates the rate at which the solidification is progressing from one point to the another. Progressing from one point to the other. Second important point, solidification rate is expressed in centimeter per second. It's very important. This is very tough. This one. Solidification rate is always expressed as centimeter per second. Solidification first one is solidification rate indicates the rate at which the solidification is progressing from one point to the other. So one point to the other means, so you can see this figure clearly understand. So this is a point number one. This is a one point to the other means this is a point one, this one is a point two. The distance point one to point two, that this is a cast part, cast before solidification, casting part, this one. There are 2 points, one and two. The one and two, the distance it is called as x. X is the thickness of the metal solidified. X is the thickness of the metal solidified. X, the distance, 1.1 to point two, the distance. X is the thickness of the metal solidified. So you can see this figure. This is the surrounding of the sand mold. The dotted line, it shows that the surrounding of the casting. This is a cavity, whatever. This is a cast part. Okay. So this is a heat extraction direction. Heat will be extracted from the component or casting. So this is the heat extraction direction. So surrounding of this casting, the sand ram, this one, foundry sand will be there. So point one to two, there are 2 points. Solidification rate indicates the rate at which the solidification in the progressing from one point to the other point. One point to the other point. So solidification one point to the other point. The distance between these 2 points, point one to point two. So it is called as x. X is the thickness of metal solidified. X is the thickness of metal solidified. Point 1 and 2 are the two adjacent point in the casting. The point 1 and 2, so it is called as two adjacent points in the casting. Point 1 and 2. So X is the thickness of the metal solidified. Solidified rate is always in expressed as centimeter per second. Solidification rate is expressed as centimeter per second. Clear? Solid rate, this one. So next you can go for temperature gradient. So the temperature gradient means, you can see the figure. So temperature gradient, so temperature, you can see here. So first figure it shows that the cooling curves at 2 points in a casting. So this is the 2 points, 1 and 2. The distance is x. This is a casting. So this one is a sand particle surrounding of this casting. Okay. So dx, dx thermocouples. Dx is a thermocouples. So distance between the two adjacent points, dx. Difference, this point 1 and 2 here. That these point 1 and 2, difference between the point 1 and 2, it is called as a distance. Distance between the two adjacent points, distance. So dt is the difference in temperature between 1 and 2. dt, T is the time. Difference, d is the difference in temperature between point and 1 and 2. Clear this point. Dx is the difference between the two adjacent points. So dt is the difference in temperature between point 1 and 2. This is the casting, and surrounding of this casting sand particles is there. And at any given time, difference in temperature between 1 and 2 at any given time. Okay. So this is a important notations used in this cooling curves at 2 points in casting. So come to this graph. So you can see graph means, you can see the this one is a temperature. Okay, temperature is a y-axis. So this is a point here. The temperature so slowly falls down. You can see here. So here, so you come to here. So this is a x1 temperature, x2, x3, x4, x5.4, and after solidification. Slowly, gradually decreases the temperature. The liquid state is converted to solid state, liquids. So slowly the temperature will be passed down here. Then after that, we'll get the solidifies or solids. So here in this figure you can see temperature. This is a individual point wise. So dx, here you can see T1, T2, T3, T4. So increasing the time, increasing the time difference. You can see this is the dt. Dt is the difference in time between 1 and 2 at any given time. At any given time, temperature between. So temperature in between the, so you can see this is the dx. Dx is the distance between the two adjacent point. This is the distance between the two adjacent point. The distance. This is a y-axis is temperature.